Hey, welcome back. This is now Calc 2, and we're worried about basic integration rules. So the basic, Calc 1 rules, you need to have those memorized. So you're looking at this table on the right. You should have all of these rules memorized except, and I'll just write out the numbers, I guess 12, 13, and then 20. But all the other ones are fair game on my tests. I warn you, your other teachers may expect you to know those other formulas. I don't know how they operate, but at least for me, you should know all of them except those. What are we going to be doing in this chapter? Basically, we're going to be teaching you how to integrate pretty much anything, and it's kind of weirdly similar to a computer program. So back in the day, they were with computers, they were always asking this question, can a computer do this? Can a computer do that? Because they hold on to this idea that like humans are somehow creative and well, in my opinion, they hold on to the idea that humans are creative and special. In my opinion, computers can do anything a human can do, and not only that, a computer can do it better. So one of those things that they were questioning was, well, human can do integration, but a computer can't. And it turns out no. One of the first sort of attempts at artificial intelligence was this integration program called SAINT, which was developed over there at MIT, and they actually gave it the freshman calculus exam, and it scored like a 96 out of 100 on that calculus exam. The programming in it is, some of it is a lot of like if-then coding, if this, then do this, if this, then do that. So it's not very technical, but if you look down in this section of the thesis, if you're interested, let me know and I'll send you the thesis. But if you look in this section, all the rules I'm having you memorize are kind of hard-coded into the computer. And there's some extra ones. This X, Y, Z are kind of different. But computers, now at this point, they literally can do it better than you. And on top of that, they can teach you how to do it, right? So you could, the computer will output the answer, because basically when a computer does an integral, it'll go through like step by step and kind of form a tree. So to show you how to do the problem, all it has to do is output all the steps in the tree. And basically that's how things like Symbolab work, and all the other integrators out there that will give you step-by-step solutions, which are, in my opinion, something that you should steer away from. But anyways, there's that. That's my little spiel. Kind of interesting to think that all you're doing is basically learning a computer program. You'll never be as good as the computer, but at least you will know what the computer is kind of doing. And right. So anyways, let's dive in here and start taking a look at some of these. Example 1, they're giving you 3 similar integrals. So here we go, example 1. Part A, the integral of 4 all over x squared plus 9. That looks like an inverse tangent, right? So the u is just plain old x. The a value is 3. We could factor out 4. So let's go ahead and factor out, oops. Oh, hold on. Right. Sorry about that. Okay, so I factored out the 4, and so I have the basic form. I'm not going to rewrite it as in terms of u. That's kind of silly. So you have x squared plus a squared. If you want to write 3 squared, that's fine, but I'm just going to write 9. And then you use the formula for the inverse tan, which is 1 over a, tan inverse of u over a plus c. So in this case, I have 4 times 1 all over a, which is 3, tan inverse, or arctan if you would rather, of u all over a. U is x all over a, which is 3, and then plus c. That would be your answer, okay? Tan inverse of x over 3 plus c. All right, then I'm going to change it up a little on you. So part B, we have something a little bit different. All you have to do is like fiddle with it a little bit and you get something different. So 4x plus all over x squared plus 9 dx. In this case, you want to do a u sub, right? When you're doing u subs, the goal, at least if you're doing like a computer program, would be to transform your collection of symbols into something that has less symbols, right? So if you do a u sub and you end up with more symbols, you did it wrong. Okay, so anyways, here you could do a u sub for the denominator. Du is then 2x dx, and then I like to solve for my d. I mean, it would be nice if we could do all of our integrals in our head, but maybe someday we'll get to that point, but not today. This is 4x all over u times dx, which is du all over 2x. I think at MIT they have integral bees, like spelling bees, except the kids do integrals. Ain't that kind of intimidating? Like they're so good at it. They just do every integral in their head. I mean, really? So anyways, the x's cancel. Get these guys are gone. 4 over 2 is 2, and then you get du over u. And then, oh, wait a second. Wait, sorry. 2 times the integral, then that's a natural log integral, right? So I'm going to go 2 ln of u. And I don't have to evaluate, so plus c, and then you back substitute and you're done, right? So this would be 2 ln, and it has to be absolute values. Absolute value of x squared, well, stand corrected. X squared plus 9 is positive, so you don't necessarily need the absolute values in this case. I just put them in anyways. I don't have time to think about all the small details, and it's not going to hurt, okay? So I just leave them in there. They removed them. Anyways, let's look at the third one. So part C, 4x squared all over x squared plus 9. Usually when I see that the numerator and denominator have the same degree, that means polynomial division. Okay. There's some tricks you can do, like you can add and subtract some sort of number, and then you'll be able to. No, I'm not going to play that game. See, if I add and subtract 36, I'd be able to get a cancellation. I mean, let me show you. I've shown you, long division before. 4x squared plus 36 minus 36, right? This sort of game. So in this case, I can then split up the fraction into 2 parts. So I'll have the integral of 4x squared plus 36 all over x squared plus 9. You see how that's going to cancel. Minus the integral of 36, which this second guy will then just be an inverse tan. So the first guy, you could factor a 4 out of the numerator. You'd be left with the x squared plus 9, and you get a nice little cancellation. Then you could factor the 36 out of the second integral. You get 1 all over x squared plus 9. That's just an inverse tan. So the first integral is 1 dx, and then the second integral, negative 36 times 1 all over a. In this case, a is 3. Tan inverse of x all over a plus the constant. And then the integral of 1 is just x, so you get 4x minus 12 tan inverse of x over 3 plus c. Okay. Yeah, so very similar looking at integrals, but then the results are different. One fun thing to do that a lot of mathematicians did back in the day was just look at patterns of integrals, so you can figure out sequences of integrals, and sometimes solve for that sequence of integrals in a way that will tell you that it's kind of the output of the particular integral if you know the form. Anyways, let's move on. Example 2. So example 2, what we're going to do is basically split the integral in half, and then we'll have 2 separate integrals. We have the integral from 0 to 1 of x plus 3 all over the square root of 4 minus x squared dx. I'm going to split it into 2 fractions again, just like I did in the last problem, really, like this. Remember, you can't do it the other way around. So if you have like x all over, or if you had like the reciprocal of that, So if you had 4 minus x squared all over x plus 3, you would not be able to split that into two fractions like this, right? That's a no-go. There's no way. You're not allowed to do that. It's only when you have this form that you're allowed to do that. It's basically the reverse of the common denominator. It's adding the numerators over the common denominator. You can reverse that process. So that has nothing to do with this other one here. This is bad. Okay, so here I'm going to split it. So the first guy is just going to be a nice u sub. You can kind of see the derivative sitting in the integral and the numerator, the derivative of the downstar part. So you're kind of always looking for two parts. You're looking for the function and its derivative. If you find that, then you could let the function be the u, and then its derivative will be the du. Okay, sort of. So let's do the u sub here, 4 minus x squared. Du will then be sort of x, right? In this case, it's negative 2x dx, so you're going to have a constant of negative 1/2 that will pop out. So you get du all over, negative du all over 2x, and then we can do our sub. The second integral is just an inverse sine, an arc sine, right? So the a value here is 2, the u is just x, so no mysteries there. That first integral, we have x all over the square root of u times negative du over 2x, and then plus what will end up being 3 sine inverse of x over a, u over a, so x over 2. Let's go ahead and factor out the negative 1/2. The x's nicely cancel. And then you have the integral of, let's rewrite the 1 over square root u as u to the negative 1/2 du. Then I can integrate, so get negative 1/2 u to negative 1/2 plus 1 is positive 1/2 times 2. And then plus 3 sine inverse of x over 2. Let's see. Negative 1/2 times 2 is negative, and then u back subbing is 4 minus x squared to the 1/2, then plus 3 sine inverse of x over 2, and then plus your integration constant. Okay. I guess we had to evaluate. Whoops, sorry about that. So let me evaluate that real quick. Put in the bar thingamajig. So I'm going from 0 to 1. Okay, sorry about that. So putting 1 into the antiderivative, I get the negative of 3 minus 1 is basically just square root of 3. Put 3 to the 1/2 plus 3 sine inverse of 1/2. For the sine function, I'm looking for values from negative pi over 2 to pi over 2 that give you 1/2. That's going to be pi over 6. So this part is pi over 6. And then minus, plug in 0, you get 4 to the 1/2. So it's minus, actually there's a negative in front of that, so minus 4 to the 1/2. And then plus 3 sine inverse of 0, which is just 0. Okay, so I get negative root 3 plus 3 pi over 6, which is pi over 2, and then plus 2 minus 0. Yeah. Okay, so there's that. Yeah, using technology is great. Substitution involving a squared. So example 3, we're basically converting something that kind of looks like maybe you could do a u sub for the 16 minus x to the 6, but you won't get the numerator. So it's more likely that you're doing some sort of sine inverse, and you'll do a u sub on the x to the 6, right? So let's try it and see what happens. You can experiment with integrals. You don't always have to get it perfect the first time, folks. So anyways, I think if we kind of note that x to the 6 is really x cubed squared, that's going to be the key to getting through this one. Or the other way around, x cubed squared. Right? Because the derivative of x cubed is sitting up there in the numerator, and you'll get a nice cancellation. So we'll let u equal x cubed. Du will be kind of the numerator. It's times a constant. 3x squared dx. So we'll have a 1/3 constant popping out. Du. So I have the integral of x squared all over the square root of 16 minus u squared times 1 all over 3x squared du. A nice cancellation. We could pull out the 1/3, and then we're just left with a inverse sine integral. Right, so 16 minus u squared. So we get 1/3 sine inverse of u all over a. In this case, a is 4. Do we have to evaluate? No, so it's a indefinite integral. Back subbing, I get 1/3 sine inverse of x cubed all over 4 plus c. Okay, great. Example 4. 1 all over 1 plus e to the x dx. Right, so how am I going to deal with this guy, right? Well, you could let the u equal the 1 plus e to the x, but that's not really going to work, right? Because, well, let's see. Let's try it anyways, right? 1 plus e to the x. Du will be e to the x dx. And then we can kind of solve for e to the x, right? Because we're going to have this e to the x floating around. Let's see if we can do it that way. Let's see if we can do it a way different than what the book does, right? Sometimes you can't. So we have 1 all over u times du all over e to the x. Okay, so what is e to the x? Well, going from this equation, e to the x will equal u minus 1. So we could rewrite this as the integral of 1 all over u times du. Well, that's not going to help very much. And we got rid of all the x material, but we've ended up with something that you're not going to be able to do until we learn how to do partial fraction decomposition. Okay, so you would be stuck here at this point until you took the rest, until you read the rest of chapter 8. What the book says to do is kind of the plus minus trick. You can also do long division. Let's do long division. I just want to do something other than what the book does. So what I'm going to do is take e to the x plus 1 and divide into, I guess, 1. So let me rewrite it. 1 plus e to the x. Okay, so it'll be like 1 times 1 plus e to the x is 1 plus e to the x, and then I subtract it. So I get minus e to the x. Well, that's not going to be very helpful either. We'll see. So your integral, starting with 1 all over 1 plus e to the x dx, is going to end up being the integral of 1 minus e to the x all over 1 plus e to the x, which is basically what they got after they did their little trick of adding and subtracting e to the x. Same thing. Then you could do a u sub on that second part. So if you split up the integral into 2 parts, then you could do a u sub on the second integral, and you'll be home free. Okay, so let's see. Let u be the denominator, because the derivative of the denominator is just the numerator. So you get dx is du all over e to the x. You get a nice cancellation. The first integral is just x minus the integral of e to the x all over u times dx, which is now du over e to the x, and there you see it. Goodbye, right? So you have x. So you have x minus the integral of du over u. That's the natural log integral. So x minus ln of the absolute value of u plus c. Back subbing, I get x minus ln absolute value of 1 plus e to the x plus c, and then you're done. Yay. Note they didn't use absolute values again because 1 plus e to the x is always positive. Some trig stuff. So example 5. These problems are starting to look more and more impossible, but they're not. In particular, the derivative of the ln of sine of x is kind of sitting there right in front of it. the cotan. So note, if you let u equal the ln of sine x, du will be 1 all over sine x times cosine x dx. And of course, cosine x all over sine x is just cotan x dx. So solving out for dx, you just get du over cotan. You'll get the perfect cancellation with no constants to worry about. So get the integral of cotan x times u times du all over cotan x. So the cotans cancel and you get u du. So you get a u squared over 2 plus c. And of course, back subbing ln of sine x, all of that squared, all over 2 plus c. It's not a big deal. Don't sweat it, I think maybe is the sort of moral of that example. Let's look at example 6. So this is using a trigonometric identity to turn it into something a little bit more familiar. In particular, if you think about the table of integrals, there's no tan squared in there, right? You got the integral, the integral of tan's in there, but there's no tan squared. But you do have the integral of secant squared, right? Number 14 is secant squared there on the right. And then you kind of think, well, I can get tan squared that equals secant squared, sort of, right? So if you start with our Pythagorean identity, sine squared plus cosine squared equals 1, divide everything by cosine squared, you get tan squared plus 1 equals secant squared. And so tan squared must be equal to secant squared minus 1. So we could do a substitution, and then we'll have two integrals that we can do. So this is going to be secant squared 2x minus 1 dx. So you can split it into two integrals if you prefer. Secant squared 2x dx minus the integral of 1 dx. And then the integral of secant squared 2x, that's just going to be tan of 2x over 2. Okay. You could do a u sub, but that's it. And then minus x plus c. So one quick way to kind of think about some integrals, so if you have like the integral of cosine of 2x dx, you probably are tempted to do a u sub, but you don't have to. The integral of cosine, of course, is going to be your sine, and then you're going to have 2x automatically. The only problem is trying to figure out what the constant is. And I'm saying the constant, all you basically have to do is divide by the derivative of the guts. So back when you took the derivatives, if you remember, like taking the derivative of sine of 2x, that would be sine of 2x times 2. So instead of multiplying, you just divide, because derivatives and integrals are kind of inverses of each other, right? So when you take the integral of sine of 2x, you don't multiply by 2. Instead, you just divide by 2. And if you do it that way, you could do a lot of integrals in your head. So integral of negative 3x dx is just going to be e to negative 3x divided by negative 3, right? Plus c. The integral of, like above, secant squared of 4x dx is just going to be tan of 4x divided by 4. You know, it's pretty simple, and you don't have to do the u sub all the time. Right? The u sub is kind of a crutch. It can slow you down to a certain extent if you're having to do millions of integrals, but in the beginning it's okay. You know, you don't have a lot to go by. You know, you're sort of a stranger in a strange land to a certain extent. But okay, so there's that. Let's see if they have any more. No. Okay, so great. So they give you some basic kind of techniques, and literally you can encode all of these into a computer and have a computer program. That's what they did back with the Saint program over there in MIT. Those programs led to like Wolfram Alpha. Like Wolfram was at Caltech, and the other guys were over there at MIT, and the Maple program was probably in there somewhere, and Wolfram Mathematica is in there somewhere. These are symbolic integrators, a little bit different than numerical integrators that just give you a number. So it's a little bit different. Okay, so anyways, maybe look at one homework. Let me see if there's any homework problems that look nasty. Of course, they're giving you crazy numbers. This one, number 5, you're going to have to complete the square on that. This one, like the example. This one, you got to do like a Pythagorean conjugate. So number 10, I'll just set it up. I'm not going to do the whole integral. D theta. The trick is to multiply top and bottom by cosine theta plus 1. Okay, so you get cosine theta minus 1, and you're going to cosine theta plus 1 and top and bottom. Okay, so what's the point of that? Well, you're going to end up being able to simplify it. You'll have 6 cosine theta plus 6 in the top. Downstairs, you got cosine squared theta minus 1. Cosine squared theta minus 1. Let's think about it again, right? So sine squared plus cosine squared equals 1. If I move the 1 over and move the sine squared over, I get cosine squared minus 1 equals sine squared. Right? So I can replace cosine squared minus 1, minus sine squared. I replace that with a minus. I'm going to move the minus to the numerator, and I get negative 6 cosine theta minus 6 all over sine squared theta. I guess I'm going to do the whole thing. Then you could bifurcate it or butterfly it or whatever you want to call it. Look at these 2 integrals. So you get a negative 6 cosine theta, and let's put that over 1 factor of the sine theta times 1 all over sine theta. So I think that's going to pay off for me. I think d theta, and then minus the integral of 6 all over sine squared theta, d theta. Okay. So that first integral is going to be a cotan cosecant. So negative 6 integral cotan theta cosecant theta, d theta, which we should know. That's just the derivative of cosecant. And then this other integral, 1 over sine squared is cosecant squared, which is another integral we should know. That's just the derivative of cotan, right? So with a negative. So this will be 6 cosecant theta plus 6, what did I say, cotan theta plus c. Okay. Let's make sure that's right. Okay. So we have 6 cosecant, I have to go to my little symbols, probably theta, plus 6 cotan theta plus capital C. That's right. Okay. And so again, for number 11, there's going to be some completing the square there. I'll go ahead and negative 1 all over x squared minus 18x plus 94 dx. Looks like it's going to be an inverse tan. So get the integral of 1 all over x squared minus 18x. And then the magic number you add in is b all over 2 squared. So b, in this case, negative 18. That'll be 81. So plus 81, immediately subtract 81, and then plus 94 dx. So it's going to be the integral of 1 all over now factor x minus 9 squared, and then sorry, I can't subtract apparently today. 13 okay. The u in this case is x minus 9, but the du is then just going to be dx. So it's kind of silly to do a sub. If you want to, you can. The a value is going to be root 13, which is why I'm flipping out, because it gave me a weird number again. All right, so I get the integral of 1 all over u squared plus 13 then du. So it's going to be arctan 1 all over a square root 13. Tan inverse of u, which is x minus 9 all over a, which is square root 13, and then plus c. Let's make sure it's right, and we'll make that the last problem. Let's make this one the video quiz. I didn't do a video quiz, so hold on. I'll do it. The next problem I do will be the video quiz. So one more problem. Just hang in there with me. We'll just go arctan of course, it's plopping it into the stupid denominator. 1 all over square root 13 arctan of fraction x minus 9 all over square root 13 plus big C, and it's wrong. Yeah, I got it. All right, so the video quiz one, let's do another complete the square. Let me mark this down for the video quiz. I apologize, I forgot about it, and I will not keep forgetting about the stupid video quiz. This will be video quiz set number 4. Okay. Of course, somehow I've run out of paper, even though I continually restock paper. This again, I forgot which quiz set I'm in. This is video quiz set number 4. And this is problem number 5 and WebAssign from 8.1. Okay, so let's chug it out. This is the video quiz, video quiz, video quiz, video quiz. And we have 15 all over the square root of 10x minus x squared dx. Plot the 15 integral of 1 all over. I want to complete the square on this thing. First to do that, I'm going to factor out a negative. So I'll have x squared minus 10x. Then I'm going to complete the square by adding in the b all over 2. So here, b over 2 squared. So negative 10 over 2 is negative 5. Negative 5 squared is 25. Then I have to immediately subtract that. But because of that negative in front, it'll look like I'm adding it, right? So if you subtract it inside those parentheses and then you distribute the negative, it would really be adding. So you're actually plus 25 at that point, okay? Dx. Then I'm going to go ahead and factor it. So I get 15 integral of 1 all over, and I'm going to use commutative law to reorder it. 25 minus x minus 5 squared dx, and then I see it's inverse signs with a value 5, and the u is x minus 5 with no, du doesn't have any constants attached, so we're free, clean and free. So it'll be 15 sine inverse of u, which is x minus 5, all over a, which is 5, and then plus c. Okay. Should I plop that in? 15 arc sine of fraction, oops, too many ofs, fraction, x minus 5 all over 5 plus c, and it's wrong. And it's, oh, I got it right. Okay, so that's the video quiz. Thank you for watching as usual, and I will see you next time.